Hello and welcome. This is going to be our lecture video for April 30th. We're talking more about probability today. So on the last worksheet, there was this question. A technician is launching fireworks near the end of a show. Of the remaining 13 fireworks, 9 are blue and 4 are red. If he launches 9 of them in a random order, what is the probability that all of them are blue? And we solve this by saying he can do 9 pick 9 ways to order those 9 fireworks divided by 13 pick 9 for the number of ways that you can pick 9 objects out of 13. And 9 pick 9 is 362,880 divided by 13 P9 gave us 0.00139, which we could convert to a percentage by moving the decimal place twice, 0.14%. All right, now this problem was set up to be pretty easy because there was 9 blue fireworks and we shot off all 9 of them. So let's change this problem to make it a little bit harder. Let's say what's the probability that he launches 8 blue and 1 red in any order. Again, grabbing 13 at random. So what we want to do is we want to just examine one case. Let's say that, so we've got, let's just write this over here. We've got 13 blue. Let me make sure we have 9 blue, 4 red. 9 blue, 4 red. So let's say the very first one we launch is blue. What's the chance of that? Well, it was a 9 out of 13 chance. The next one we launch, we'll say it's another blue. That was an 8 in 12 chance because one firework is gone and one of the blues is gone. All right, next, let's say he grabs the red. So that was a 4 in 11 chance. And now he's got to shoot nothing but blues for the remaining 6. So 7 out of 10, 6 out of 9, 5 out of 8, 4 out of 7. We've shot off 4, 5, 6, 7, 8. And then he's got a 2/5 chance for that last one being a red. Okay, so this will give us the exact probability that he shoots off 2 blue. So it went blue, blue, then a red, and then 2, 3, 4, 5, 6, 7, 6 more blue. All right, but what if that red happened earlier? So if that red happened earlier, then that would have been like a 4 in 13 chance. And then we would have resumed 9 in 12, ... All of these numbers that are on top would still be on top. They would just be in a different order. And all of these numbers on the bottom would still be there in the same order. 13, 12, 11, 10, 9, 8, 7, 6, 5. All right, so that red can happen in 9 different spots. So I want to take this probability and add it to itself 9 times to represent each of the different spots the red could be in, because that specific scenario will have the same probability as all the other scenarios. So I'm just going to figure out what this is here. So I'll do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 4 to get the top, divided by 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 on the bottom. And yet that this specific scenario has a 0.00 5, 6 chance of happening. And then I'm going to multiply it by times 9 for the 9 different spots red can be in. Write that. So times 9 gives me 0.05035. Just leave it at that. Convert that into a percentage times 100%, and we get a 5% chance. So very unlikely that he shoots off all blue, but if we give him the option to shoot off one red, we go up to a 5% chance. Okay, let's change it again. Let's say what's the probability that he does 7 blue and 2 red. All right, so I don't have to write out all of these numbers again. So what I'm going to do is for the 7 blue, that's going to be a 9 pick 7 calculation. Let me think about that for a second. Yes. So that's the number of ways to pick the blue. And then for the reds, that's going to be a 4 pick 2. All right, so that's going to be my numerator divided by 13 pick 9. And then I get to multiply all of this by 9, little 9, choose 2 for which fireworks are red. So let me just check a few things. 4 pick 2, that should be 4 times 3, that should be 12, and it is 12. All right, so let me plug this all into my calculator and see what I get. So I'm going to multiply that by 9 pick 7, got a very big number, divide that by 13 pick 9, multiply that by 9, choose 2, and I get 0.302, multiply that by 100%. And so this is the far more likely scenario, a 30% chance that of those 9, he shoots off 2 red and 7 blue. All right, and we could keep going all the way up to the probability of shooting off all of the reds. So 4 reds and 5 blues. And then we could check and see if all of those probabilities still added up to 100%. And that'd be a good way to check that we're doing this right. I'm going to write up that math right now. I'll pause the video and we'll see if we add up to 100%. All right, and here's my math for 6 blue, 3 red, 47% chance. 5 blue, 4 red is an 18% chance. I was a little surprised by this because I thought it'd be a little bit more rare to shoot off all 4 of the reds. I felt like, good chance that one of them gets left behind, but 18% chance. It's the probability of shooting off all blues that's the real outlier at not even 1% chance. If you add everything else up, it does come to 100%. So that's a sign that we're doing this math right. All right, I'll include this math in the slideshow if you want to look at it closer, but we got other stuff to talk about today. Goal is to be able to determine if 2 events are independent, dependent, or mutually exclusive. You got to know these 3 vocab words. And why are we doing this? To calculate the probability of compound events. So a compound event is two or more events. At once, or in one improbability, we'll say. So we want to be able to calculate the chance that it's raining and I didn't bring an umbrella. So that'd be a compound event. All right, if you want to follow along, it's page 439. I'm pretty close to the end of that book. And let's start with the definition of mutually exclusive. So mutually exclusive events are events that cannot happen at the same time. All right. So, example, a coin landing heads and tails. All right, heads and tails are mutually exclusive. So a coin landing heads and tails is impossible. So these are the mutually exclusive events. All right, now not every probability is mutually exclusive. A good example of something that's not mutually exclusive is drawing a card from a deck, the probability that it's a 7 and the probability that it's a heart. Those things can happen at the same time. You can get the 7 of hearts, or you can get just the 7, like a 7 of spades, or you can get just a heart, like the queen of hearts. So it's possible, so there's some overlap where it's both, in both categories, those are mutually exclusive. A coin can only land on either heads, tails. I guess technically it can land on its edge, but that would be another mutually exclusive event to heads and tails. They can't happen at the same time. All right, so as a picture, this is what it looks like. Here's our sample space. The sample space is always a rectangle for some reason. At least that's how I learned it. Your sample space. And then events are always circles inside that rectangle. So here's event A, and here's event B. And they are mutually exclusive because there's no overlap. All right, let's talk about some probability notation. So the probability of A and B equals 0. So this symbol here, it's like a big N. It means and. All right, and there's another way we can write this. The probability of A or B, and or is a big U. It's an upside down one of these symbols. It's normally drawn just like a little bit different than a capital U. It is its own key on the keyboard, or at least in the symbols. But the probability of A or B is the same as the probability of A plus the probability of B. Let's talk about why this makes sense. So this means or. So if there was some intersection here, then the probability of either or would actually be less than their combined probabilities because that overlap doesn't get counted twice. Here there is no overlap, so you get the full chance of probability A plus the full chance of probability B. Okay, independent events. This is very often confused with mutually exclusive. You need to understand that there's a difference here. Independent events is that when two events happen in order, this is like the most important part right here. there has to be some sort of ordered quality to it. It has to be event 1 happens, then event 2 happens. So when 2 events happen in order, the outcome of the first event doesn't affect the outcome of the second. All right, so an example of this, we'll go back to flipping coins again. It does not matter what your last coin flip was. You could have flipped 10 heads in a row. That doesn't mean that you're any more or less likely to flip a head on the next flip. What happened before does not affect what's going to happen next. So let's see what sort of notation we want to write with independent events. Let's see what the book has. Yeah. So what they say is, for the notation, is the probability of A and B is equal to the probability of A times the probability of B. And this is how probability should normally work. You know, if you got a 1/2 chance and a 1/2 chance, them happening together is 1/4, as long as they're independent. Dependent is where it gets kind of confusing. Okay. I don't want to say anything else about independent events. I'm just reading what it says in the book. Let me see what it said about mutually exclusive events. No outcomes in common. Okay. Yep, I think that's good. So a dependent event. This is a scenario in which the outcome of one event influences the probability of another event. A scenario in which the outcome of one event influences the probability of another event. Let's see what the book says on dependent events. Does it have a definition? No, I don't see a definition here. So let's try to think of an example to understand dependent events. So, our firework example is a really good one. Whether or not I shoot off a blue rocket or a red rocket first influences the probability that I'll be able to shoot off another blue or red rocket. So anywhere where we're using up some sort of resource. So we'll say, drawing an ace decreases the probability of drawing another ace, because there's one less ace in the deck to pick from. If you've already got 3 of the aces, the chance that you're going to draw the 4th one is super low because there's only 1 ace left in the deck. So that would be a dependent event. All right, and so with independent and dependent, they both have a temporal quality where event 1 happens, then event 2 happens. All right, the complement of event. This is the probability that an event does not occur. And it's got a special notation. So if the probability of some event A is 40%, the probability of A's complement, so A not happening, has to be 60%. And that's because of this formula here, the probability of some event A plus the probability of that event's complement has to equal 1, because something has to happen. It either has to happen or not happen. One of these two will be true. And then we can rearrange this to find other probabilities. But I think that's good for complement of an event. Let's talk about our last problem. It's on the bottom of page 442. When comparing the market shares of two products, a marketing director states that the probability that a customer will pick brand A is 0.43. The probability that a customer will pick brand B is 0.46. And the probability that the customer will pick neither brand is 0.14. A person at the meeting questions these probabilities. Why? So again, something has to happen here. We either have to pick brand A, brand B, or neither. And so that these probabilities should add up. So the probability of A plus the probability of B plus the probability of the complement of the union of A and B should equal 1. So 0.43 plus 0.46 plus 0.14. What do these add up to? 0.43 plus 0.46 plus 0.14 is 1.03 equals 1. So what's going on here? Is this data bad? Well, not necessarily. So we're in a situation where these three probabilities add up to 103% chance, but that could mean that there's a 3% overlap here. Could mean 3% will pick both. So they get both the Frosted Flakes and the Cheerios. It's not all that many people if you only have those two options, not that many people will get both. But that could explain why this is adding up to over 100%, because some of this, 3% here is also being counted over here. But this person, if these are mutually exclusive events, then this person has every right to question these probabilities because they're not adding up to 100%. All right, there's a worksheet to work on. That's that for this video. Have a good rest of your day.